Hello, friends. It's good to see you. Happy Halloween. Believe it or not, I am in costume. Would anyone like to guess what I am? Close. It's actually the opposite of that. This is Dr. Mama. So if you run into me on the weekend, this is what I will look like when I'm not being Dr. Lisa. And normally, if it's hot, like it is right now in this room, I will also be rocking pigtails because my hair is too short to put in a single ponytail. So I'm just going to go with the full-on look here. The name came about when my son Huey was somewhere between 1 and 2. One day his dad told him that, did you know Mommy's a doctor too? Because we were talking about going to the doctor's office. And from about a good 2 to 3 months, he called me Dr. Mama exclusively. Even first thing in the morning, Dr. Mama. That was what I got to wake up to. And then, of course, his dad said, did you know that Daddy's a doctor too? And he said, no. No. Daddy's not a doctor. And the reason he thought that, my hypothesis was, is that he goes to a pediatrician's office, Lawrence Pediatrics, where all of the doctors are women. So in his world, men aren't doctors. That's just crazy, right? Which I think is sort of cool, right, in a very modern sort of way. But yeah, I'm Dr. Mama today. So that's what I'm rocking. I told you I was going to take this opportunity to be lazy. And what's better than loungewear while you're working, right? Just one step above PJs. So welcome. Happy Halloween. Is anybody going to do anything fun tonight? No? Do what? You froze them on Halloween? Oh, that is just really unfortunate. Well, I'm not sure what we're going to do. Huey wasn't feeling all that great this morning, so we'll see what he has the energy for. He's probably going to want to trick-or-treat and just hoard the candy. He doesn't actually want to open it. He just likes the little colorful packages. So we'll see what happens. But in the meantime, we have a brand new topic, measurement invariance. So the good news is that you already know how to do this. There's nothing new about these procedures. The only thing that you have to learn is a new set of vocabulary. And the vocabulary differs as a function of which kind of measurement model you're using. So we'll start with CFA, so we're going back to the world of item intercepts, factor loadings, and residual variances, a linear prediction from the factor of the item response that's supposed to be continuous, and then eventually we'll head back to IRT and IFA, in which this same idea is referred to as a different name with a different set of terminology. But it's all kind of the same idea. So first off, definitions. What are we talking about? Measurement invariance goes by several synonyms, factorial invariance, or more simply, measurement equivalence. It's the idea that the items that you have measure the trait in the same way across either groups, occasions, or conditions. So it's not that your groups don't differ in the trait or that people don't change in the trait over time. It's the way the items relate to the trait is the same. To the extent that the items relate to the trait in the same way, then you can interpret group or occasion differences in the trait as real. And that's what's known as structural invariance. So what we want is no difference. We want to be able to say that our measure works the same way across populations or across time. That way we can make those kinds of comparisons at the trait level and feel confident about that. So when would you want to know this? Pretty much any time that you are using a measure for a population or a sample for which it was not intended. That happens pretty frequently. So if you have a, let's say, Heather, you work with, what's your mom affection measure thing? Okay. Okay, so you have a population that it was intended for or developed for of moms and their adult children. You are using it for a different kind of population, mom and adolescents with Fragile X. So this would be relevant to you, whether or not the items work the same way. Whenever you're testing something longitudinally, you're assuming measurement invariance, whether you recognize it or not, if you're using the same items to measure the same trait over time. and any other kind of repeated measures type factor. So if you have a condition manipulation, that would hold true as well. When we get to IRT and IFA, the same ideas will apply, but with a different terminology and a different direction. So this same idea of whether or not the items relate to their trait the same way is called differential item functioning in IRT, but it's backwards. So measurement invariance is non-differential item functioning, and people call it diff. Measurement non-invariance is called diff. Just, because, right? Non-invariance is a mouthful. You'd think it would be just measurement variance, but it's not. It's non-invariance in the terminology. When I talk about this to people who are not in this sort of world, I usually try to say equivalence because I think that makes more sense from a layperson point of view. And that's why I throw that term in here as a synonym. So we're going to test group differences in the measurement model parameters, which in CFA, item intercepts, factor loadings, and residual variances. So we need to get to a point that is known as partial measurement invariance at a minimum, where at least some of the parameters can be constrained. That way the model can still be identified equally across groups. After that, if you want to, you can test something called structural invariance. And since the structural model is factor variances, means, and covariances, that's what is of issue. And so those, if they exist, can be construed as real differences. Legit differences between groups in the trait being measured, such as what is it again? Mother-child relationship. So yes, there, that's a mouthful too. Mother something, how's that? So there's two different ways in terms of how to go about setting up these models to test this, and it depends on whether or not your groups are independent or dependent. So if the groups are independent, so like two separate samples of people that have nothing to do with each other, what we're going to do is set up a model that has each group separately but run it simultaneously. And then in a series of constraints, say that the groups need to share parameters. Identical idea, but a different setup happens if you have dependent groups. So if you have paired data, like spouses, or moms and kids, or time 1 and time 2, or a repeated measures experiment where you have control and then they go through a treatment, something like that, where it's the same something measured repeatedly, then all of the factors have to be into the same model. So I have an example for you of both of these types of analyses. It'll be 7A and 7B respectively. And you have to use the second kind if you have dependent data, because you have to be able to account for the fact that the traits from the same unit, family, person, whatever, are going to be correlated. So you have to build that into the model. So here's what a picture would look like for that latter kind of setup. So this is from your textbook. He has an example of 4 indicators measuring job satisfaction at time 1 and time 2. So he would set this up as a 2-factor model. There is a covariance between the factors that always stays there, because how you are at time 1 is likely related to how you are at time 2. In addition, the same item at different occasions usually gets a residual covariance by default, because we assume that there's something specific about that item that would cause people to answer the same way across time, above and beyond the trait. You don't have to put those in. Only when there are identified residual variances in the model can you put them in, such as when in CFA or when you're using WLSMV. You can test whether they're significant and get rid of them if you want to save parameters, but that's usually something that you can add and no one will question it. All right, so are we ready to do this? Why not? So here's our first model here. This is where we're going to start from. So this is the same example we had in CFA. I have a 2-factor example in the slides and a 1-factor example in our handout. So we'll go through these step by step. So we've got 3 indicators each for 2 different factors. So this is what it would look like for a single group. I've identified my model such that each factor has a mean of 0 and a variance of 1. That way I can estimate all of my loadings and all of my intercepts. So step 0 then in this process is debatable in terms of whether or not you would actually bother to do this, and that's testing the entire covariance matrix as a whole. So each group has a set of item means, item variances, and item covariances. You can do an omnibus test of whether all that stuff simultaneously is the same across groups. And if it is, you can say, I'm done. But I don't particularly think that that test would be helpful. If you're testing everything at once, it's somewhat of an average comparison. You could still have pockets of differences between groups that you wouldn't necessarily see. So I don't know that that test is terribly useful, and therefore I don't bother to do it. In addition, there's some controversy as to whether you start top-down or bottom-up, meaning start from a model where everything is the same across groups and slowly let things be relaxed so that each group gets their own, versus starting from a model where both groups get everything separate and slowly constraining. I favor the latter. There's no guarantee that you would necessarily end up at the same place, but you might hope that you would. So here is a bottom-up approach, starting with a model, not a covariance matrix. This is what it would look like if we had 2 factors, 6 indicators, where indicator is the same as item, 3 per factor, and 2 groups. So the total number of parameters that we could have, that's the total number of item means, which are going to become item intercepts, item variances, which are going to become item residual variances, and item covariances, which are going to be predicted by factor loadings. So there's a formula to figure out what the total number of pieces of information going in is, pieces of data, and it's the number of indicators times the number of indicators plus 1 divided by 2 plus the number of indicators again to capture the means. So in this case, if we have 6 indicators, that's 6 times 7 is 42, divided by 2 is 21, plus 6 is 27. So each group has 27 pieces of information going into this analysis, and that means we have 54 total across 2 groups. And yes, you can do this for more than 2 groups. It just gets more complicated in terms of the number of steps you'd have to go through. Okay, so the very first step then, configural invariance is what this is called. It's just fitting the same type of factor model in each group. So a 3-factor model or a 2-factor model. And I say same, it's like ish. You could have maybe a residual covariance in one group and not in the other, or little tweaks like that, but the same indicators should map onto the same factors, otherwise game over. It doesn't make sense to test invariance of a factor if the factor is defined differently. So you want to hope that whatever factor structure you end up with fits reasonably well within each group before going forward. So at this point, the groups share nothing. It's as if you're just running 2 models, one for each group, but you're doing it simultaneously, and all of your fit statistics are combined. So this then, since it's the most complicated model, each group gets their own everything. Everything from this point, we're going to be seeing if our constraints make it not worse. We're going to be simplifying, taking parameters away. So a significant change in fit is a bad thing. It means the groups differ. A non-significant change in fit is a good thing. It means the groups can share parameters. So we'll do the same thing that we had done in the world of CFA to test differences in fit, nested model comparisons via likelihood ratio tests. So we're still using MLR, which means you can't just take the straight -2 log likelihood difference. You have to use the scaling factors. There's a link to the website where they describe this. We'll still use the same spreadsheet that I built you for example 4. I've got a new one for example 7A, and it will follow the same process, by which I have it here. You enter your -2 log likelihood for the HO model, that's yours, the scaling factor that goes with it, and the number of free parameters. Make sure the model that has fewer parameters is on the top, and the model that has more parameters is on the bottom, and then your test statistics should be right there. So this spreadsheet is up online for you to refer to. All right. Okay. With me so far? Yeah? Good enough? Okay. here's what it would look like then in terms of seeing an equation to describe the model. Sometimes equations are helpful. I find them helpful in tracking exactly what's changing across these things. So I'm using subscripts here to convey which factor, or excuse me, which loading, try this again, which set of parameters in which group. So the first subscript is which item. The second subscript is which group, a 1 or a 2. So at this point, we have Y item group, because each group has their own set of items. They share items, but they have their own set of responses. And all of the parameters after that have both subscripts. That means the groups don't share anything. So the first term is the intercept. That's mu per item per group. Next thing is the factor loading per item per group times the factor, so it's either factor 1 or factor 2 in this case, and then the residual per item per group. So we're estimating everything. In order to have the model be identified, to make sure that our traits each have a scale, I've fixed both the factor means to 0 and both factor variances to 1. So at this point, it's like we've within group standardized. The parameters for the items are not comparable across groups because we've re-standardized to have a mean 0 and variance 1 within each group. So we can't look at those parameters easily and determine whether or not there's group differences because they're not on the same scale yet. So if we go through the list of total parameters, 54 possible, that's 2 groups times 6 intercepts, 6 variances, residual variances, and doing the math in my head, very dangerous, 15 covariances. We're going to spend 38 parameters to get those, 12 intercepts, 12 residual variances, 12 loadings, no factor variances, 2 factor covariances because each factor for each group gets a separate covariance, and no factor means. So then we end up with 16 left over. So this is as good as it gets. This is configural. So let's look at an example. So I'm going to pull up example 7a so that we can walk through the M+ code for how you would do this. As I said, the slides have a 2-factor model to be more general. This is only 1 factor, but in our next example, we'll get to do 3. So it will ramp up the complexity as we get going. So this example came from your textbook, actually. I borrowed his example. Interestingly, I did not come to the same conclusion as him, even though I analyzed the same data. So what happens in textbooks a lot of the time is that this process goes perfectly. So have you read this chapter yet? Anybody? No? I'll spoil it for you. Everything's perfectly invariant. It's amazing. That is not going to happen to you, ever. Let me just tell you that right now. The only situation in which that may happen is if you're dealing with a very, very small sample. So what happens to statistical power in small samples? Good or bad? Bad, right? So in this case, it's power to detect a difference. So if you have bad power, you can't tell that the groups differ in these parameters. So this is an instance in which if you're really hoping that the parameters are invariant across groups, having a small sample will help you find that, or not find differences. So that's the one case in which everything may work perfectly, is if you have no power to detect differences. This sample, though, is big enough probably not to have that problem. I am quite certain these data are fake because there are exactly 345 people in each group. And it is a scale that goes from 1 to 9 about indices of depression here, and it fits perfectly as a unidimensional model. So here is the input for everything that we're going to do. This will stay the same across all the models. The M+ outputs that go with each of the models is online for you if you want to see what each of these looks like as a full set of output. So once again, we have all the variables in the data set on names. The first variable is our grouping variable, which indicates differences between men and women. We're going to use item 1 through item 9. Here's a new one. Grouping. That's how you tell it how your groups are organized. So you first list the variable that differentiates one group from another, and then you can provide labels. So whatever labels you provide here will show up in your output. So it's helpful to give yourself some breadcrumbs. Rather than group 1 and group 2, you can label it as something that you'll remember what it means, men versus women in this case. So women are the reference and men are the alternative group. We specify missing data. We're back to MLR because we're in the world of CFA. Mod indices 3.84. That means print all of the suggestions for improving the model, which we will use when we're testing invariance, that would improve the model by a p less than 0.05 for 1 degree of freedom. So that's the chi-square value that goes with 1 degree of freedom. We're looking at the standardized solution and the residual solution, although at this point we would have already fit the model and decided that a one-factor model was good enough, so we won't have to pay attention to too much of that. Okay. Questions so far? So I have a note here. There's going to be 2 model statements. There's different ways to set up these different invariance models, and M+ in the manual has lots of examples of how one might do this. I'm picking the one that might require more typing but is more clear to understand. Once you understand the process, you can start finding ways to take shortcuts to shorten the amount of code that you have to write, but for now we'll make it as clear as possible. So what's going to happen is that every time you see model, that is specifically for the reference group. Then we're going to have model men that describes how the model differs in the men's group. So here on the next page then would be a configural model. Configural meaning everything gets to be what it wants in terms of the item parameters. The scale is within group specific at this point. So on the left is the model. So this is specifically for the women now, because I also have model men. And no, this doesn't turn blue, and I don't know why. You would think it did because it's model, but it doesn't. So don't worry if you see that and it doesn't work for you. So everything from that point on is exactly like you may remember. But note that I have done something on the women's side that I have not done on the men's side. Labels. Yeah. So at this point, because I have labels on the women's side and no labels on the men's side, that means that all the parameters get to differ. I'm slowly going to add labels to the men's side to constrain parts of the model one at a time. So on the women's side, we have item 1 to item 9. The star at the end overrides the default that makes the first loading 1, so we're estimating the first loading instead. L1 to L9 means I'd like all 9 loadings. I'm just labeling them 1 to 9. Likewise, we're back in CFA, so we have 9 intercepts. We also have 9 residual variances. In this particular data set, he had a residual covariance between item 1 and 2. And then we've identified our factor, which is called depress, with a variance of 1, mean 0. And everything looks the same on this side. Okay. Questions on the setup? Okay. So here's our fit. Looks the same as usual with a few distinctions. So which are we, HO or H1? We're HO. We are the hoe, always. So 56 parameters. That's because we have 28 parameters in each group. We have 2 chi-square contributions. So the total chi-square is this 94 thing. That's how far off our HO is from the H1, but it's combined across groups. And then it tells you down here what the contribution of the chi-square is for each group. These numbers are only directly comparable if your groups are of the same size. Otherwise, the bigger group contributes more. It has to. because the chi-square value is a function of sample size. Then we get our RMSEA and our CFI TLI. So is this a good model or a not so good model? That's a softball. You think good? Yeah? 1 vote for good? Looks good? The only thing that would be bad would be the chi-square test of model fit, which pretty much is never going to be non-significant, especially not with that many degrees of freedom. So we have, by the way, do you know where the 28 came from? 56 divided by 2? Do you want to review that? Yeah? How many items do we have? 9. How many parameters per item are we estimating? Yep. Each item gets an intercept, a loading, and a residual variance. So 9 times 3 is 27, but I said 28. What'd I forget? What did I forget? There's a residual covariance. That's the one more. Yep. So 28 in each group, 56 total. How many more could I have estimated? Is that number on here somewhere? Well, the total, remember, comes from the formula 9 times 9 plus 1, which is 10, over 2. So that's 90 divided by 2 is 45, plus 9 equals 54. And we have 2 groups. So that's 108 total. We just spent 56. Because remember, number of free parameters means number of estimated parameters. They're free to be not 0. That's what that means. And, oh boy, trying to do math from 2nd grade on the board. Thank goodness I didn't have to borrow. 52, right? Does that look right? Do you see 52 up there somewhere? Yeah? Katie, where is it? Yeah, that's what that means. Left over. Number of things I could have added and didn't. That's the definition of degrees of freedom. And it boils down to pieces of data in, parameters coming out, and the difference. So while I don't have absolute fit, as indicated by this p-value right here, meaning H1 is significantly taller than HO, I do have close fit, meaning that my RMSEA is not different than 0.05. In addition, I have decent CFI and TLI values, and so he had declared that this model was good enough to start with. So I took the factor loadings and the factor loadings for right now, and I made a picture. This is just plotting what is on the output on the next page here. That's where those came from. So in the output, you will see labels that you had written. So starting off is group women. Following that will be group men. And again, you can label these however you like. It's going to steal the labels that you put right here in group equals. So there's the factor loadings. There's the residual covariance. Factor mean is both 0 in both groups for identification. There's all the intercepts, which in this case is going to be the item means, given that the factor mean is 0. Factor variance is 1 in both groups. Residual variances differ across groups. So let's look at the pattern of loadings. Eyeball them, because that's what we're going to focus on next. Do you see any general trends here? Women are red, men are blue.
Where women are higher in the factor loading, they're much higher? They're higher?
Generally, it looks like women are higher in some items, but not all. So 6 is an exception. 7, they look pretty close. So the question then is it the case that these items work better in women? Or is it the case that women have a different amount of trait variance than men? And once we correct for that, these things are proportionately reduced. Right now, we're assuming that the trait is the same, so we can't directly compare the loadings. But the next step in this process is to see to what extent this pattern of differences in loadings is the result of differences in factor variance. The next step is called metric invariance. So there's another synonym for this step. It's called weak invariance. Yeah, and these names got made up a long time ago, and I'm just teaching you them because people may use them. When I do this in papers, which is not all that frequently, but when I have, I never just say weak or metric. It's always metric invariance, i.e. equality of the loadings, right? Don't make people remember their vocabulary. They may not have ever seen it. But equality of the factor loadings is a concept that they can understand. So it's not that we're testing tau equivalence. We're not taking the loadings and seeing if they're all the same within a factor. We're saying, is item 1 in group 1 the same as item 1 in group 2? Can I make that same item share a loading between groups and not have the model fit worse? That will be true for all the loadings to the extent that these differences are proportionate. So we have to change the factor variance in the alternative group when we do this step. Now, you will find that the way I am teaching you to do this is different than the way that it is done more commonly, and even the way that it's done in your textbook, but there's a reason for it, and if you ever want to cite it, there's a paper that you can borrow. It may be on your reading list. If not, I can track it down. But normally speaking, what people do is fix the first factor loading to 1 to identify the model, right? Remember that as an alternative? Hello? Remember? Do I need to get out a picture? Would that help? Yes? Why not? See, I've got all my pictures. All you have to do is ask. Is there another, like, Halloween parade going on out there? Okay. Say, if anybody wants to go watch the kiddos, I won't be offended. Let me get a picture. Tyler's like, nope, I'm going to get enough of that later. Yeah. Remember this picture? This is lecture 4. Different ways to identify the model. So the M+ default and the most common way of doing it is the top right corner there, where the first factor loading is fixed to 1, and the factor variance is estimated instead. So to identify the variance side of the model, you have to fix something to 1, either a loading of an item or the factor variance. Likewise, to identify the mean side of the model, you have to fix something to 0, either one of the intercepts or the factor mean. And the combination of factor mean 0 but factor variance estimated is by far most common, and that's the version that you have to have if your factor is going to be an outcome downstream, because then its variance has to be free to become leftover variance after it's predicted by other stuff. So people start with that in their invariance testing, which is fine for the configural model. It doesn't matter how your model is identified. The fit will be the same, and all the parameters will just rearrange themselves. Remember Happy Birthday? It's the same song no matter what key you started in. That's the idea. Identification doesn't really matter. But when we get to invariance, it matters. So if I did it this way, where the second and third loadings were estimated and the first loading was fixed to 1, I could test the constraint that item 2 shares a loading across groups and item 3 shares a loading across groups. But what about item 1? If I fix it to 1 in group 1 and I fix it to 1 in group 2, can I test whether 1 equals 1? No. I'm assuming it does. So if you happen to pick a marker item that is non-invariant, it really should be different between groups, but you've locked it in to be 1 for identification, everything else gets messed up. So that's why I don't do it this way. What I do instead is this in the alternative group, or the reference group. The reference group factor variance stays at 1 to identify both groups simultaneously. I will then test each of the loading constraints by estimating all the loadings. This one right here. So the reference group, their factor variance is still fixed to 1. All the loadings are then constrained to be equal across groups, and the reference group factor variance is 1. The alternative group factor variance is estimated. Then it can differ from 1. So in terms of the equation for the model, I've highlighted in bold what has changed. Each factor loading that multiplies the F factor does not have a group subscript anymore. It only has an item subscript. So item 1's factor loading is different from item 2's is different from item 3's, but item 1's factor loading is the same for group 1 as it is for group 2. So group 1 basically is setting the scale of the model, because they're the ones that have the factor variances fixed to 1 for identification. Both groups still have their factor means fixed to 0 because they're not sharing intercepts yet. That's coming next. And we would still estimate both factor covariances in each group as well. So let's try it. Here's model 2A. Let's play Where's Waldo? The women's model is exactly the same. I just pasted it here so that you'd have something to compare against. What has changed in the men's model? Factor variance in capital letters can now be freely estimated. What else? Why can it be freely estimated? Because I constrain the loadings, and how did I do that? I added the same label. The sharing of the label is what makes it constrained. So in the same way that when we tested tau equivalence, the same factor loadings across an item, we just said loading, and we had one word, and that meant all the things on that line had to share it. Whenever you have the same term in different places, that means the parameter is constrained to be equal, is being shared. So now both groups are contributing to the estimation for the loading of each item. So I just got a chance to review a paper that was basically a report of how frequently measurement invariance is screwed up in practice. It was like a review article. And it varied by journal, unsurprisingly. But the most common thing that people screwed up in this step, as well as the one that follows, is this right here. That's why I tried to put it in capital letters. You cannot forget to release the constraint for the factor variance being 1. It has to be estimated. That way, the factor variance can absorb whatever differences there were in the loadings. Otherwise, you're introducing both a measurement constraint and a structural constraint simultaneously, and that's no good. So don't forget this part right here. And I would do that for each factor in the model. All factors in the alternative group get their variances freed. All factors in the reference group get their variance set to 1. So now, relative to my configural everything gets to be different model, I had 56 parameters. I have fewer. 56 minus 48 is 8, right? I'm killing second grade math today. That might even be first grade math, I'm not sure. Any educators in here? Anyone? What? Second grade? Okay, I'm killing second grade math. I don't remember much else from second grade, like geography or history or, you know, the difference between a peninsula and archipelago, like all that kind of stuff is gone. But I can retain, you know, addition and subtraction of two-digit numbers. So, 8. No, is that what I said? Yeah, 8. We have 8 fewer parameters. That comes from 9 loadings. So it should be 9, but I had to give one back to estimate the factor variance. So I took away 9 loadings, but I added a factor variance in the alternative group. That's a net change of 8. So in this case, I'm going from a more complicated model that has 56 parameters to a simpler version where some of the loadings are shared. That's 48. So these are nested models, and I'm going to do a likelihood ratio test, -2 log likelihood difference, to see if they fit differently. What are the 2 choices of what can happen? Relative to the configural bigger model, my metric invariant simpler model can fit significantly worse or not worse, non-significantly not worse. Yes. The whole next 3 weeks, it's worse or not worse almost exclusively because we're starting from bigger and narrowing down. The exception to that is if you look at the RMSEA, which actually can get better as you simplify the model, because RMSEA is per degree of freedom. So as you add back degrees of freedom, it can like your model better because it's more parsimonious. But in an absolute sense, the -2 log likelihood will always go down if you take away parameters. The question is, did it go down a lot, which is bad, meaning that they shouldn't have been shared, or just a little bit? So at each step, you do want to check sort of how your absolute fit is doing. So my RMSEA was 0.047, CFI was 0.63, or 963, 966, 042. So these things actually indicate the model is a little bit better because it's simpler. So I'm not hurting any of these things. But to test more formally whether or not I've hurt my model fit, I pulled out my handy-dandy spreadsheet. I believe in Levon that they have a thing for this, don't they? What's it's called ANOVA? Okay, that makes more sense. Okay, someone said ANOVA in their write-up, and I was like, that's not an ANOVA. But okay, if they call it that, then my bad. Sorry, Mayumi, if she's listening from Japan. Yeah. My bad. I didn't know what she was talking about. I have no idea what they call it ANOVA, but whatever. That's neither here nor there. So here's my first comparison. Note that metric goes in the top and configural goes in the bottom. Fewer minus more. So the scale difference in chi-square, or the scale difference in -2 log likelihood, that is your chi-square. That's 4 on 8 degrees of freedom. P-value non-significant. So my metric model fits. Say it with me. Not worse. Good news or bad news? Good news if I want to measure depression using the same items in men and women, because that means they can share their loadings. So how each item relates to the trait is the same across groups. That's good news. Now, what if it didn't work out that way? Well, this is where your Voodoo is actually going to help you. So we'll see this as an example in the next one where metric invariance falls apart, and we'll see this in scalar here shortly. But the Voodoo gives you its usual suggestion for model improvements, error covariances, cross-loadings, and whatnot. But it also gives you the parameters that you constrain back as well. So if I saw a modification index suggestion for item 1's loading on the factor, I'd be like, Item 1 already has a loading on the factor. What? It's like, no, it's telling you it wants a different one in this group. It's telling you that the constraint that you just made broke your model significantly. So even though it's somewhat data-driven and suspect to all the usual concerns about that, it does give you a sense of where to go next if this test fails, if the model does fit significantly worse. Fortunately, in our case, it was okay. So next is scalar. So we did loadings first. Now we're doing intercepts. So the term for this is scalar invariance or strong. So metric is weak, scalar is strong. And so this is a very common thing to get misunderstood. So I want to spend a little bit more time on this one. The intercept for each item is not necessarily the item mean. We've talked about this before, but it bears repeating. Let me give you an example of what I'm talking about here from the world of regression. So I'm writing y equals beta 0 plus e versus y equals beta 0 plus beta 1 times x plus e. The difference between these two beta zeros, one's a mean, one's an intercept. If there's no predictors, then beta 0 becomes the grand mean of y. If you don't know anything else, your best guess for someone's expected value is the mean. If you do know something else, then this mean becomes an intercept. It becomes conditional. So you can say it's a conditional mean or an intercept, whereas this is a marginal mean. Conditional mean is the expected value of y when x is 0. When we're doing this, we are not testing the item means, the first one. We are testing the item intercepts. So it's not that both groups have to have the same means. That's not the deal. It's that both groups have to have the same expected value for people who have a trait score of 0. In other words, there should be no reason beyond the trait that your score changes. It shouldn't matter which group you're in. It should matter what your trait is. And so to the extent that there's group differences in the trait, that then trickles down to cause your intercept. But group directly does not affect the intercept. So let me show you a picture here. I made this picture from the output of the metric model, where all of the intercepts are allowed to differ between men and women. At this point, the model does not address group differences in the factor, in the trait. So we've done the loadings and addressed group differences in factor variance in doing so. We've allowed them, but the factor means are still the same. So again, staring at this chart here, women in pink, men in green. Do you see any general tendencies? Visual analysis, if you will. You can totally make shit up. It's okay. Go for it. Women are a little higher on everything, except for maybe 1, right? And 5, I guess. Those are low. So are just women more depressed? I don't know. It could be that women are more depressed, and that's what's causing this difference that shows up in all the intercepts. Or it could be that women have a higher expected score, even if their depression is the same as a man. So that's what we're trying to figure out. Are these differences proportional? After controlling for factor mean differences, would they go away? That's our question. So that's the test of scalar invariance. So we're moving down then in terms of an identification where the factor mean in the alternative group is going to have to be freed to answer that question. So at this stage, The group subscripts have been taken off the intercepts. So each item still gets a different intercept, but the intercept per item is shared across groups. Group 1 is still identifying the model via its constraints on the factors. The reference group still has all factor variances fixed to 1, still has all factor means fixed to 0. But after we constrain the intercepts to be equal across groups, whatever differences were there in the intercepts should be allowed to be showed up as a factor mean difference. So we let the factor mean in the alternative group be free instead. And in this case, because there's two factors, there's two factor means to be worried about. So here's a picture that helps to illustrate why it is the case that the way that this process goes is like a single elimination tournament. You start with loadings. If an item gets knocked out first round because its loading needs to be different across groups, it's done. You typically don't test any more constraints on it. Here's why. So these 4 pictures then, also taken from your textbook, illustrate the combinations of an item achieving metric invariance or scalar invariance or not. So here in the top left, what makes it so that this item, I can say that it has metric invariance based on the picture? You tell me. The slope is the same. Metric is factor loadings. Factor loadings are slopes. So to the best of his drawing ability, those are parallel or equal slopes. Over here, yes, metric still, equal slopes, no scalar. This, by the way, is squiggle, a popular choice for either a random effect or a latent trait. My latent traits are called F because I can draw that reliably on the board, but this is a squiggle where 0 is the mean and the variance is 1. So how does this picture show that there is a lack of scalar invariance? Different intercepts, yes. So at the same value of squiggle, the expected y depends on which group you're in. So there is something about that item that makes groups differ above and beyond trait differences. Down here in the bottom 2, these show a case where there may or may not be scalar invariance, and it depends on where your factor mean or where your factor is 0. So if your slopes differ, your intercepts could differ for that reason alone, because the intercept is the expected value when your trait is 0. So if you look at the bottom left picture here, if I had made it so that my trait was 0, say, over here, those intercepts may not be different, but the fact that I have non-parallel lines means that eventually there's going to be a difference at a certain point on the trait. It's the same idea that you can't talk about a main effect when you have an interaction term. It's the main effect specifically when the other variable is 0. So if you have an item that fails metric, meaning the slopes are non-parallel, typically it is the case to skip testing the intercept because the intercepts could be different because the slopes are different, not otherwise. That's the typical practice. There's nothing wrong with testing the intercepts if you want to. If they happen to be the same, then you could constrain them and save a parameter, but that's the typical tournament approach to this kind of thing. Okay, does that make sense? Any of that you want to hear again? So we're testing intercepts, not means, for the items. So this was the results from the metric model that made this picture here. Note that at every step of the process, you want to eyeball your results and make sure that the constraints that you wanted are actually being applied. So this is my metric model in which all of the loadings should be the same. The factor variance should be different. And in fact, it is smaller in women relative to men, at least numerically. So here's my scalar model here. Two things different. In the men model. Maybe I should have brought candy and started chucking it at people. I'll try that next week if I'm here. The intercepts are constrained. That's the I1 to I9, now shared across the two sets of code. And what else did I do? Because I constrained the intercepts, I had to... Yeah, don't forget that one. You're asking the factor mean to absorb whatever differences in the intercepts were there. Have to let it go. Otherwise, you're doing a measurement constraint and a structural constraint at the same time. So previous model, where just the loadings were constrained, was 48. Now we're down to 40. Change of 8 because we had 9 intercepts, but we had to give a factor mean back for a net change of 8 degrees of freedom. Go to my handy-dandy spreadsheet. And this is what I get. On 8 degrees of freedom, a chi-square lends itself to a p-value of 0.13. And this is the point at which your textbook author said, yep, non-significant, we're done. 0.13 is fairly non-significant, right? No one would argue that's trending or approaching. But here's why I say we might not be done. The difference between absolute local or global and local fit. Remember the report card? A difference of 12 could be because most of them had a difference of about 1, and one of them had a difference of 4. So an average across 8 of 12 does not preclude a few of them from lending most of the differences between models in terms of fit. So I want to do the analog of checking local fit just to make sure that I haven't missed anything in testing 8 things at the same time. And that's where our friend the Voodoo can help. So in the modification indices, I've only shown you the ones that are relevant for testing invariance. So I'm disregarding any other suggestions with respect to residual covariances and whatnot. Okay, good. So we get these two things here. That for the women, there's a modification index of 5.8 for item 7, something very similar in the men, and there is a difference in the expected parameter given right here. So what this is saying is that the model would be improved by a chi-square of like 5 if I relax the constraint on item 7 that the intercept be shared between groups. And it's trying to anticipate what the new intercept would be. So on the next page is the scalar invariant solution. Item 7 was constrained to have an intercept of 3.711 in both groups. The Voodoo is telling me, actually the women, they want to have a higher intercept by 0.16, and the men want to have a lower intercept by -0.2. And if you made that happen, your model would improve by this much. So 5.8 is the expected change, 5.9, something like that. The entire change for all 8 degrees of freedom was 12. So half of the difference in model fit, misfit rather, half of the difference in the change in fit is due to one item. And the other half is shared across the 7. To me, that's problematic. So I'm going to deviate from the textbook example to let item 7 be free. So I'm on page 8. The way I did that is to change the label for item 7. So item 7's intercept in the women is still going to be called I7, according to M+. In the men, it is called I7M. It doesn't matter what it is, it just needs to be different. So now we're back up to 41 parameters. And this is the point at which two different model comparisons would be relevant. So if I compare back to the previous model, where item 7 and all the other items had intercepts that were forced to be the same, but now I've relaxed the constraint and let them be different, I've made my model bigger. When you add stuff to your model, what can happen? Well, if you take stuff away and it's worse or not worse, then if you add stuff, better not better. So I can compare relative to the previous model to see if I'm headed in the right direction. So that's the next comparison that I did. And note that I'm trying to make it easier for you to keep track. I have worse or better as the model test. So there's my chi-square of 5.9, just as was predicted. So yes, it did help to free item 7's intercept. Model fits significantly better than the alternative in which item 7's intercept was constrained along with all the others. If I now take my new and improved scalar model and compare it back to metric, you can see that it is not worse by a much bigger margin. So I was able to reduce half of the change in misfit by freeing that one item. So the terminology then, if not all of the items can be constrained, but some of them can, is partial whatever. So at this point, we constrained all 9 loadings, so that's full metric invariance. We constrained 8 out of 9 intercepts. We would call that partial scalar invariance. And that's why I have these models labeled 2A, 3A, and 3B. I have a different number for each step and then a different letter for each model within that step. So how partial can partial be is not something that anyone has decided. 8 out of 9 is pretty good. Technically speaking, mathematically, you only need 1 for the model, the items to still be linked across groups. But if only 1 item out of 9 can share its intercept, that should make you very squishy. At what point you want to be squishy? I don't know, 2/3, 3/4, just most would be good. Because what it means if you can't have it be constrained is that something other than the trait is causing differences in those item means. So the more items you have like that, the less you can interpret the trait means as reflecting the thing you're thinking that it is. So in this case, what is item 7? Item 7 is higher in women than men. So at a trait level of 0, women have an expected response of 3.7, whereas men have an expected response of 3.5. Item 7 happens to be feelings of worthlessness or guilt. So women are more likely to feel worthless or guilty at the same level of depression. I'll set aside the political commentary, but it's right there in the made-up data. Or maybe it's not made up, I don't know. Or it was made up to show a pattern. Now, whether or not you want to make a big deal out of a difference between 3.5 and 3.3 on a scale of 1 to 9, it's significant. We have a big enough sample to call a difference of 0.2 on a 9-point scale significant. Whether practically speaking you want to worry about that, it's a judgment call. But when you're in the situation where you're finding things that are non-invariant, don't just say non-invariant. Say what the pattern is. Item 7's intercept differed between men and women such that women had an expected score that was higher than men's at the same level of the trait by 0.2. So now we can answer the question, are women more depressed? Were the original differences in those item intercepts, which were item means at that point, due to depression? (3B). Here's the mean for women. It's fixed to 0 for identification. And here's the mean for men. It's free to be not 0. So the mean for men should only be interpreted as a factor mean difference. The scale is arbitrary. But we know that on average, men have trait scores that are less by 0.1-ish, and that's not different than 0. So it looks like men are not less depressed than women, significantly so. But the thing about item 7 is that now we can't say that item 7 is contributing to whatever gender mean difference there is in the factor, because it's been relegated off. By freeing those intercepts, we're taking it out of the factor mean. Last one for measurement invariance, residual variance. This one is subject to even more debate as to whether or not it's important. Residual variance is whatever not the factor is. You can test whether each group has the same amount of not the factor. It is important to test both loadings and intercepts if you want to compare factor variances or predict factors or compare factor means. It's of debatable importance whether you can still do so if your residual variance test fails. But here's how we would do it. Model 4A, we've added to the residual variance line the labels for the women's group. Note item 7. I'm starting out by kicking item 7 out of the tournament. Because it failed scalar, we don't test it for residual. It could have different residual variance because it has a different intercept. There's nothing I have to do with respect to the factors at this point. I freed the factor variance when I fixed the loadings. I freed the factor mean when I fixed the intercepts. I don't have to do anything factor. Difference in -2 log likelihood relative to my partial scalar model. And this is why I think the data are made up. This will never happen to you in life. No. Not the factor is almost always different across items, at least some of them. So particularly if your items are on a 9-point scale. But in his world, they're not different. So at this point, in the entire measurement model, of the 27 parameters we've tested, only one differs between groups. The intercept for item 7. Hooray. The last one that we haven't tested is the residual covariance between item 1 and 2. I fill that in here by adding the label. Look at the change in fit. It does fit significantly worse, and so we're going to not constrain that residual covariance before moving on. So then in total, 2 parameters out of 28 couldn't be shared. That's pretty good. Very good, in fact. So then I would have the blessing of the universe to go forth and look at gender differences in depression at the trait level, to see whether or not women and men are differently depressed, whether things predict their depression differently, and so forth. Ta-da! You can test some of that without looking at the relationships with other things at the level of structural invariance, which is where we will pick up next time if I am able to come. So here is the plan for Monday morning. I am going to try and be as undesirable as possible during my jury selection process, and I'm going to have an email queued up on my phone to everybody, and if they let me go, then I'll tell you that we're having class. If you don't hear from me, I'm not going to be able to be here, but Jihong's going to be here. That way he can help you with homework 4. So we'll have just open lab hours from 1:15 to 4 on Monday if I'm not here. But if I'm able to make it, I will let you know, hopefully before like 12 or something. That would be the absolute cutoff. Okay? All right. Then I'm going to be here for a little bit longer and then try to go to my son's Halloween parade at his school. And have a good evening, folks. I will hopefully see you next week. If you have homework questions, since I didn't ask, please come ask them before I leave.